4-3 standards revolve around the sharing of electrons. So we're talking about covalent bonds, either pure covalent or polar covalent, and how we can visualize how they are put together, as well as what they would be doing in three-dimensional space rather than the two-dimensional space that we'll start doing some diagramming on. So a Lewis structure shows how many bonds or valence electrons there are between atoms in a molecule. And we have some steps to drawing them. First of all, we want to determine the total number of valence electrons in the molecule. This is important because this will be a step that we'll go back to at the end to verify that we've created the correct molecule. Then we'll determine which is the central atom. And we'll do that by looking at the atoms and the number of valence electrons that they have to start with. So I would look and see which one has the least number of valence electrons, and that would be the one at the center. Another way to look at it would be to look at how many total atoms of each molecule or each atom I have, and see which one has the least number of atoms. For instance, H2O has only one oxygen. The oxygen would be at the center rather than the two hydrogen, because there's two of them, there's more of them. And then we'll do a check to make sure that every atom has 8, with the exception of hydrogen. Hydrogen is in that first energy level, and the first energy level can only hold 2 electrons. So hydrogen is only looking to get to 2 rather than 8. So it's not looking to get to the octet rule like every other atom will be. And we'll again check that total at the end. So that's that last check. We counted them at the front. Now we'll check them at the end. So let's try one. We have phosphorus trifluoride. Remember, our rules when we're dealing with covalent molecules is we don't crisscross. We're not looking at charges because they're not based on electrostatic attraction between charged particles. We're looking at the electrostatic attraction between the shared electrons and the positive cations that are left with, or the positive nuclei that are left within it. So we don't crisscross anything. Since there's nothing in front of the phosphorus, that means I have one of them. Since I have tri, that means I have 3 fluorines. So I have PF3, and I've got to do my check first of how many total electrons there are. So I look at my periodic table, and I look at the number of valence electrons each of these have. So phosphorus is in the 15th group. It has 5 valence electrons. Fluorine is in the 17th group. It has 7 electrons, but there's 3 of them. So to get my total, I'm going to have to multiply 3 by the number of valence electrons I have. 3 times 7 is 21. Then I'm going to take these two numbers, 5 and 26, and get my total by adding them together for 26. My central atom is going to be the phosphorus because it needs 3 more. Each of these fluorines only need 1 more to get to 8. So phosphorus needs 3 more to get to 8, fluorine needs 1 more to get to 8, and my other way of looking at it is that there's only 1 phosphorus, there's 3 fluorines, so I put the one that I have least atoms of in the middle. So I'm going to put my phosphorus here. I just cleared off the stuff on the left side there to save some space. And then I'm going to start putting dots around the phosphorus to represent the number of valence electrons that I have. So I'm going to have 5 dots around phosphorus. Now there's some rules to doing these dots, and one way to visualize it is to imagine that there's a square around the phosphorus, or that my phosphorus is in a 2-dimensional box. And on each side of my square rectangle that I have, I would have at maximum 2 dots. Which makes a lot of sense because if I have a square that has 4 sides and 2 dots max per side, then the maximum I'm going to get is 8 and meets that octet rule. And one of the ways that scientists do this until they start getting in the habit of visualizing where the molecule is going to end, they'll just start at the top left corner of their box and they'll put their first dot down. And then they'll do one on the second side, and so we'll get 1 on each side to start with. Now I've got 4, but I need to get to 5, so I'm going to put 1 more up here for now. So there's my phosphorus. I'm going to start adding my fluorines in. So I'll put a fluorine over here to start with. I could have put it over here or over here. I wouldn't have put it up here though because there's already 2 electrons here. I wouldn't be able to form a bond with that, so I wouldn't put one up there. So I'm going to start 1, 2, 3, 4, 5, 6, 7 for fluorine. Now I'm going to pop in my other 2 fluorines quicker. With these though, I'm already starting to visualize what's going to be happening. I know that I'm going to be having a bond here. I know I'm going to have a bond here, so I'm not going to want to double up like I have here with my fluorine. So I'm going to put in my fluorine there, and just thinking ahead, I'm going to put my singleton at the top because I know eventually there's going to be a bond there. If you don't know that at this point though, that's okay. You can start out the same way we did with this one, so it would look exactly like that. We would just have to do more erasing as time goes on. And here's that last fluorine. So now I've got all my 1 phosphorus and my 3 fluorines, each of the fluorines starting out with 7 valence electrons, my phosphorus starting out with 5. Now I'm going to start making some bonds between them because right now they're not bonded, they're not sharing their electrons at all. So what I'm going to do is say that this phosphorus is going to share this electron with this fluorine and this electron. And so rather than having a dirty little dot and dot, I'm going to put a nice straight line between the phosphorus and the fluorine. And we want it to be a nice straight line. Don't just connect the dots. Actually erase the old dots, put in a nice straight line in between. I'm going to do the same thing right here. This phosphorus is going to share this electron with this fluorine's electron right here. We're going to clean it up. And then I'm going to have this phosphorus sharing this electron with this fluorine's extra electron there, or single electron there. And now I've got 3 beautiful lines, each of those lines representing the 2 electrons that are shared. This is called a single bond. Single bonds are sharing 2 electrons between the atoms. So if I just imagine looking at this fluorine right here, and I want to count to check the octet to make sure it meets the octet rule, I would count the 2 electrons that are shared between phosphorus and fluorine. So I have 2, 3, 4, 5, 6, 7, 8. So that fluorine's good. It meets my octet check. And I'm going to check this fluorine. It's got the 2 that's being shared, so 2, 3, 4, 5, 6, 7, 8. That one has 8 as well. Let's check this fluorine. 2, 3, 4, 5, 6, 7, 8. So that's good. Now all I have to check is my phosphorus. So each of these is again being shared, so this phosphorus feels the effects of 2, 4, 6, 7, 8 electrons. So each of them meet my octet check. Now I need to check that they all meet my total number, so that they all are 26. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. I've met my octet check. I have a beautiful 2-dimensional representation, Lewis structure of my, or Lewis dot diagram is another word for it, of my phosphorus trifluoride. Let's try carbon tetrahydride, which is also called methane, and we'll get more into why that is called methane when we get to organic chemistry at the end of the school year. So I have 1 carbon, 4 hydrogens. Let's remember what tetra stands for, 4 hydrogens. So I have CH4. Each carbon starts with 4 valence electrons because it's in the 14th column according to the IUPAC. The hydrogens in the first column, it has 1, and there are 4 of them, so that's 4 total from the hydrogens. And that's going to give me a total of 8 for CH4. So that's what I'm going to look at for my total. Now remember, hydrogen does not want to get to 8, it wants to get to 2. Therefore, that is not what needs the most electrons. It is actually the carbon that needs the most. Carbon needs 4 more electrons. So my central atom will be carbon. I'm going to put carbon in the middle. I've already put the 4 dots around it, representing those 4 valence electrons that carbon has. And then I'm going to start putting hydrogens around it, each of them having 1 valence electron. we can already see that we're going to be sharing some electrons, like that electron with that electron being shared between the carbon and the hydrogen. And then we have that electron and that electron, those will be shared, the two there, the two there. Got a nice cleaned up molecule. Again, I erased those dirty looking ones. I've got nice straight lines. It looks much cleaner and it's easy to represent and visualize what's going on. So I have, we'll do some checks. So the hydrogens are just looking to get to 2. So my octet check for these hydrogens are just for 2. And that hydrogen feels the effect of those 2 electrons. So that's 2. That hydrogen feels 2. That hydrogen feels 2. That hydrogen feels 2. So all of my hydrogens are good. Now let's check the central atom, the carbon. It has the feeling of 2, 4, 6, 8 electrons around it. So those meet my octet checks. I'm going to do the total check. 2, 4, 6, 8. Sure enough, there are 8. That does meet our total check. That's my carbon tetrahydride. Oxygen, this is on its own, so we always ask ourselves, what is it, a diatomic molecule? And sure enough, it is one of those magical 7, so it's O2. So I'm going to look at where it is on the periodic table. It has 6 valence electrons. It's in the 16th column. So I have 2 times 6 is 12, so I'm going to look for a total of 12 electrons. And we've been doing a lot with single bonds so far, so we're going to put it like that. And I'm going to ask you, is that the correct diagram for my oxygen? They each feel 8, 2, 4, 6, 8, 2, 4, 6, 8. But we have 2, 4, 6, 8, 10, 12, 14. That's 2 more than I need. So that means I'm going to have to share more electrons, and this is where we're going to get a double bond. So instead of sharing 2 electrons, I'm going to be sharing 4 electrons between them. And so I have, for each one, an octet check. 1, 2, 3, 4, 5, 6, 7, 8. That meets my octet. 1, 2, 3, 4, 5, 6, 7, 8. That meets my octet. And then let's see if I have 12 overall now. 2, 4, 6, 8, 10, 12. Sure enough, I do. So oxygen, O2, is not singly bonded, it's doubly bonded. And just a little note over here that a central atom doesn't count or doesn't apply here because they're just 2 of the atoms. I don't have one thing in the middle with things surrounding it. I just have 2 atoms side by side. Now nitrogen. Again, it's an element that's on its own, so I ask myself, is it a diatomic molecule? Sure enough, nitrogen is. It's N2. So I have 2 times N. Nitrogen is in the 15th column. It has 5 valence electrons, so 2 times 5 is 10. My total, 10 valence electrons that I'm looking to get. Again, there's no central atom. It's not applicable in this instance. So I put them side by side. And this way, it'll only work if I have a triple bond, because I would have, if I had single or double bond, I'd have too many electrons around it to meet the octet rule. So I'm going to have 6 electrons being shared this time rather than 4. Dihydrogen monoxide, our good old friend water. So the di is telling us that I have 2 hydrogens. The monoxide means I have 1 oxygen. And again, we don't crisscross unless we're dealing with ions or an ionic compound. So I have H2O. I have 1 oxygen that has 6 valence electrons. I have 2 hydrogen, each with 1 valence electron, so that's a 2 total. 6 plus 2 is 8, and my central atom is going to be oxygen because it needs more electrons than hydrogen does. Plus, there's only 1 atom of oxygen, and there's 2 atoms of hydrogen. My molecule would look like that. And the reason I put them on corners next to each other is a little bit of foreshadowing to what we're going to get to in our next section of these notes, which is the Vesper theory. And that's where we look at what happens in 3-dimensional space. In 3-dimensional space, we've got electron clouds of unpaired electrons that are pushing away in 3 dimensions my hydrogens. And so that's why I draw it this way, rather than putting one of the hydrogens on the opposite side of the other hydrogen. So again, I'm foreshadowing, getting us ready for what we're actually going to be seeing in three-dimensional space. There are some special cases. The octet rule isn't always followed. We have some small molecules like beryllium chloride or beryllium dichloride and boron trifluoride, and those are ones that don't have enough space for the unpaired electrons. We also have what's called a dative or coordinate covalent bond, in which one atom donates both electrons to the single bond. And it works the same as a regular single covalent bond. It just seems like we're doing a little bit of magic when we put them together, because we're using two of the electrons from one atom to be what's being shared between it and another atom. And sometimes we represent this when we're drawing it out with an arrow going from the atom or the species that is sharing both electrons to the one that doesn't have any of the shared electrons. So we sometimes do that, but in general at this point we can just do a line between them as we would with any other bond. It just seems like we're doing a little bit of magic while we're making the bonds. Let's do one with an ion, because sometimes these polyatomic ions that are have a net overall charge and can be used in an ionic compound, they're going to be bonded covalently. So my ammonium ion, just like a carbonate ion or a sulfate ion or a phosphate ion, those are going to be bonded within that part covalently, and then with that net charge could bond to something else ionically. So we'll look at nitrogen. Nitrogen is in the 15th column, so it has 5 valence electrons. Hydrogen is in the first column. It has 1 valence electron, but there's 4 of them, so that's going to give us a total of 4. And then I look at this charge here. A 1 plus charge means that I have lost an electron, so I'm going to subtract 1 from my total. So I have not 9, but 8 total. My central atom is the nitrogen because it needs the most. So I put my nitrogen in the middle, I put my hydrogens around it, and then what I do when I have a polyatomic ion is I put it in brackets, and then I put whatever the charge is on the outside. And then this would then again be bonded ionically to something else. And we're going to stop here for this section of the notes and continue on in a moment or on a different video with why do they have different shapes.